Now it's time to write the equations for a four-bar linkage. And compared to a slider crank, it's actually a lot easier, even though we need to start with the kinematics table for a triple pendulum instead of a double pendulum. So if we think back to what we had with the kinematics table, again, depending when you're doing this, this is either a review from months ago or maybe a review from a day ago. But if you think back to what we had a triple pendulum problem where point B we said was pinned, right? There was our B for base, P for point, then we went Q and R. We had length R1, length R2, length R3, and then we had our angles of just simply theta, phi, and psi. So you've seen that before, and you can go back to the reviews or to your class notes. But what is the difference between a four-bar linkage and this triple pendulum? So remember a four-bar linkage back from when we did mobility or degree of freedom, we said there's 1 degree of freedom. One of the reasons we like it. If we rotate the first link, everything moves. We know how everything moves. We just have to control one thing. So what's the difference? If we focus on R, we see that point R, to a pen, point R is pinned. The fact that B is pinned, we actually built into our equations, if you remember from the first kinematics table. So if we pin it, it can't translate, it can only rotate. So if you've just reviewed the slider crank, you might be able to figure this out. We have two constraint equations. So constraints for a four-bar. So if you look at R, the velocity, the scalar equation, V at point R in the x direction is 0, and V R Y is equal to 0. So that's this right here. So this here is our first equation. If I pull out the scalar equation, right, the minus R1 theta dot sine theta minus R2 phi dot sine theta, sine phi, I'm sorry, minus R3 psi dot sine psi is equal to 0, and similarly, this is our second equation. That's it. Two equations for every four-bar. That's if I only care about velocities. If I care about accelerations, then acceleration of capital R in the x direction is 0, Ry is equal to 0, right? So this whole mess here is 0. That's a scalar equation. If I extract this one here, oops, is equal to 0. So I have, in this case, potentially 4 equations, so I can handle up to 4 unknowns. So what do we have? Let's maybe work over here so I can zoom in a little bit. So if I just look at my first two equations, if I only care about velocities, what do I have? I have R1, yep, dead spot again, try it again, R1, a little bit better, maybe not. I have length R2, I have length R3. I have theta, I have phi, and I have psi. That spot again. Theta dot, phi dot, psi dot. Okay, that's if I just have velocities. So, and I have two equations, so I have maximum 2 unknowns. So if I look at these, let's say I look at this four-bar linkage right here. I know the length of R1, and let's just remember R1 is between the pins, not the outer length. R2 is between the pins, and the same thing R3. That's what we're measuring, pin to pin. So if I have it in front of me in some position, as long as I have it in one position, I'm good to go. So I can measure R1, R2, and R3, or look it up. What about my angles? Let's just remember, theta is defined from this positive x-axis. This is theta. Maybe that's 45 degrees. Phi is this angle in here, I don't know, maybe 10 degrees, but be really careful about psi. Remember, it's defined from Q to R. So it's from here all the way around. This is my psi. So whatever that is. Similarly, let's look at this other one. So here's another four-bar. So what do we say, right? R1 is pin to pin, easy. R2 is pin to pin. R3, what's my theta? Theta there, I don't know, maybe 30 degrees. Let's pretend that's horizontal. Phi is here, right? So it's maybe 300 degrees or minus 60, mathematically is the same. And then Q to R, this one's a little bit easier. Oops, not doing very well with horizontals. And who knows, maybe 30 degrees. So just be really careful with the angles that we have. So let's go back to our unknowns, or knowns. So we said, so we know R1, if we have it in front of us, we know R2, we know we know R3. Similarly, it's in front of us, we can find the angles. I have two equations, two unknown. Remember, it's 1 degree of freedom, pretty easy. So typically, is the angular velocity of the first link or the third link, could be the middle link, but typically it's one or the other. So let's just say I'm given this one. That's it, two equations, two unknowns. I can solve for that, pretty easy. If I care about acceleration, then I'm also using these right here, acceleration of Rx, acceleration of Ry. So what are the other variables buried in these equations here? So I also see in there, I see a theta double dot, I see a phi double dot, and I see a psi double dot. The first I already have from my first two equations. So I have two more equations, I can handle two more knowns. Typically, if theta dot is given, the angular velocity, then the angular acceleration would be given. And then I can solve for these two. Let's open it up a little bit. So I can solve, as I said, for, let's say, phi double dot and psi double dot. And as I said in the past reviews and you've been taught in class, let's just remember that when you see a theta dot outside, it's in radians per time. You see angular acceleration is in radians per time squared. You have to convert. And we also use counterclockwise as positive. So if you are told that something is 20 RPM clockwise and counterclockwise is positive, then not only do you need to put a negative in front of it, you need to convert from revolutions to radians. And what is it? One revolution is 2 pi radians. So 20 RPM clockwise, if that happens to be our theta dot, let's say, right over here, theta dot would equal minus 20 revolutions per minute, and then one revolution is 2 pi radians. And we'll get radians per minute. Maybe I need to convert to seconds. It doesn't really matter. But this is it. So let me zoom back in here. And for any 4-bar, I have these 4 scalar equations. Right? This one here equals 0. This one here equals 0. And same thing for the acceleration.